In this video, we are going to analyze the Galois group of the polynomial t to the power of 6 minus 7 over q. To do so, the first step will be to find the roots, which we will find by combining the Galois theorem with Euler formula. Which will give us that the different roots of this polynomial are going to be the sixth square root of 7 multiplied by e to I to pk divided by 6. From here we will just define alpha to be the sixth square root of 7 and theta to be e to 2pi divided by 6, so that when we square or we power theta to various values, integer values, we go over the different k values here and we go over the different roots. So then our roots are a combination of alpha and theta, which is alpha, then alpha multiplied by theta, alpha multiplied by theta to the power of 2, alpha multiplied by theta to the power of 3, alpha theta to the 4th, and finally alpha theta to the 5th. Actually, this is the primitive sixth root of unity. And actually, we can write this in a more succinct shape. So alpha multiplied by theta to the power of k when k goes from 0 to 5, both included. Now, we know that then the splitting field for this polynomial will need to include both alpha and theta, so we can already write this. This will be q adjoined with alpha and theta. Now, next question that we might ask ourselves is, which is the degree of the field extension that we have here, which is the field extension of joining alpha and theta to q. So let's find that. By the Tower of Law, we know that we can simplify this and split it into two parts. One is the extension over alpha joined to q, and then the small extension of alpha joined to q over q. So we need to find these two smaller extensions, and then just by multiplying their degrees, we obtain the degree of the biggest one. So to do so, we're going to, let's enumerate this. Let's first find this degree. So to find the degree of q adjoined with alpha over q of this field extension, what we will do is we will first find which is the minimal polynomial of alpha over q, and then we know by the field theory that the degree of this minimal polynomial is actually the degree of this field extension. So okay, the minimal polynomial of alpha over q. Let's find this. This polynomial is an irreducible polynomial which has alpha as one of the roots. So we know that the original polynomial that we had here, f, has as one of the roots alpha. Now the question that we need to answer is this polynomial irreducible over q? Let's find out. To do so, we are going to use the Eisenstein Einstein criterion, which says that first we need to find some Q such that in the first case it does not divide a sub n, then it does divide a sub I from 0 to a sub n minus 1, and then third condition, the square of this Q should not divide a sub 0. Okay, let's use this. So let's say, so we know that this is the polynomial that we are analyzing. We will need to find kind of these relations. We can already smell that, like, if we use 7 as Q, things might fit. I mean, other numbers might not, but 7 looks like a good candidate. So let's use that. Let Q equal 7. Then, so the first one is 7 does not divide a sub n, which is 1. Okay, check, pass. This is true. I mean, it's not a divisor. Then, second question, does 7 divide minus 7, 0, 0, and the rest of zeros? Yes, it divides them. And then the third one, does the square root, does the square of 7, which is 49, not divide a sub 1, a sub 0, which in our case is minus 7? Yes, this is also a pass. Thus, f of t being t to the 6 minus 7 is irreducible over Q. Now we are going to use this polynomial as our first minimal polynomial, which is t to the 6 minus 7. This polynomial has degree 6, and by all the theory that we know that then the degree of Q adjoint with alpha over Q is the degree of this polynomial, which is 6. So we found like the first degree, which is the degree of this extension. Now let's go for the second extension. For the second extension, we want to find the minimal polynomial of theta over Q adjoint with alpha. Since we are here, so this is the base field, and then we adjoin theta. So we want to find the minimal polynomial of this theta over the base field. So there is a trick here, which is that we know that theta is the primitive 6th root of unity. And the consequence that this has is that the minimal polynomial is the 6th cyclotomic polynomial, which has the shape as we write in the following. Usually we use phi to denote these kind of cyclotomic polynomials. So the 6th cyclotomic polynomial has the shape of t to the power of 2 minus t plus 1. And it has as roots plus and minus theta. So we are going to say that this is our second minimal polynomial. And then, as before, when we want to know the degree of alpha and theta adjoined to Q over Q with adjoined to alpha, this is equal to the degree of this second polynomial, second minimal polynomial, which is the cyclotomic polynomial, which has degree 2. So with this, now we can already conclude which is the total degree of this field extension, alpha and theta adjoining to Q over Q. So this is 2 multiplied by 6, which is 12. This is what we were trying to do here, just that now we just replaced, like here we put the actual concrete value of the degree, which is 2, and here the other degree, which is 6. 2 multiplied by 6, 12. This is also the order of the Galois group of this extension. And what this tells us is that we will have 12 Q-automorphisms of this group, which we are going to find now, turning the page. So okay, so let's find the 12 Q-automorphisms. So, okay, 12 Q-automorphisms. As a just it's in the other page in the so okay, let's find the 12 Q-automorphisms. So just a recall, we have the first minimal polynomial that we found was t to the 6 minus 7, and the second one is t to the 2 minus t plus 1. Here the roots are alpha theta to the k from 0 to 5, and here the roots are plus minus theta, which is the same as saying plus theta to the power of plus minus 1. All right, so this is just to keep it here. Now, the Q-automorphisms that we want to find need to fix one of the elements that we have in this field extension, alpha and theta. So we want one Q-automorphism that fixes alpha and axon theta, and then another Q-automorphism which fixes theta and axon alpha. So let's start by defining sigma, which fixes theta. This is fixed, and takes action on alpha. Now, what we need to find is that, okay, so we have alpha. The minimal polynomial of alpha that we found is this m sub I, which is t to the 6 minus 7, which has all those 6 roots. So this Q-automorphism, sigma, will act on alpha by sending alpha to another one of the roots of this minimal polynomial, which we have all those possibilities: alpha, alpha theta, alpha theta squared, alpha theta to the cube, alpha theta to the power of 4, and alpha theta to the power of 5. We are going to choose alpha theta. So what we will have is actually alpha is being sent to alpha theta. Because now if you keep applying sigma to alpha theta, what you will have is alpha theta theta, which is alpha to the power of 2. Sorry, alpha theta to the power of 2. Now if you have alpha theta to the power of 2 and you apply again sigma, you will find that now you have alpha theta to the cube. And doing so, you keep iterating. And once you reach the alpha theta to the power of 5, you apply sigma, and then you will get alpha theta to the power of 6, which is the same as going back to alpha. Why? Because if we do, and by theory we know that since theta is a root of unity, a sixth root of unity, when we reach the sixth one, the theta to the power of 6, we will go back to 1. But we can also see this visually. So we start here with alpha. We know that all those roots of this polynomial are so we have this component of theta, which is like the sixth root of unity. So to draw the sixth roots of unity, it's just a matter of like dividing the unity circle into six equally spaced points. So we have here alpha theta. Here we have alpha theta squared. Here we have alpha theta to the cube, alpha theta to the fourth, and alpha theta to the fifth. Now, those are the six roots of this polynomial. And what we are defining here is this sigma, which it's applied in this way. So you have alpha, you apply sigma, and then you land into alpha theta. Now, if you have alpha theta and you apply sigma, what you will have is alpha theta theta, which is alpha theta squared, and you can keep going on. So this is applying sigma, 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 and sigma. All right. So we found one of those Q-automorphisms. Let's find the other one that we have. Let's say tau. So we want tau to fix alpha, and we want tau to act on theta. Now, to act on theta it means to send theta to another root of the minimal polynomial of theta, which is this polynomial, and the options are plus, minus, theta. So since we are already in theta, what we want is to send theta to minus theta, which is the same as saying theta to the power of minus 1. So, in other words, what we have here, these two Q-automorphisms, we can also combine them. So let's write the final combination of them. We have sigma to the power of k combined with tau to the power of j. And when you apply this to alpha, this has the effect of sending alpha to the power alpha multiplied by theta to the power of k for k in between 0 and 5, both included. And when we apply this combination of Q-automorphisms to theta, this is sending theta to the power of j, with j being plus minus 1. Okay, so this already tells us that here we will have, so this allows us for 6 combinations, 6 options. Like so you have 6 different elements that you can pull here, and this allows us for 2 options, which when combining them, what you get is 12 combinations, which this matches the 12 Q-automorphisms that we want to find. So the set of Q-automorphisms that we want to find is just the combination of these 2 Q-automorphisms and their powers, so that we obtain the 12 Q-automorphisms. In the drawing that we had before, doing tau means to just flip, because tau is just sending theta to the power negated, which means that if you are here, you do theta to the power of minus 1, which is equal to theta to the power of 5. So it's like sending this point to this point. Then when you are here, it's negating this, which means that you go back here, and same for here. And then alpha and alpha to the alpha multiplied by theta to the power of 3, they are unaffected by tau. So this tau is like when you just flip the entire board, and you over this axis. So what we can conclude is that the Galois group of this polynomial is generated by sigma and tau. And also we can conclude another thing, which is that if we have all these rotations and then also this flip, this reflection mapping, this usually has the smell. So we have reflection, rotation, then we have reflection, and all the elements are spaced in a regular distance. This is usually with the smell of the group of symmetries, the diagonal group, in this case, diagonal group of order 12, which is denoted by this V with a 6. And this is isomorphic to our Galois group. So our Galois group is isomorphic to the diagonal group of order 12, D6. And in fact, we can kind of draw these lines in between all the roots of our polynomial. And you see that here we have this hexagon. Usually when we have these n-gons and with the rotation and reflection, this is okay, we are in this diagonal group. But furthermore, you can try to, so in order to continue from here, it helps, at least to me, it helps to visualize this in a more like 3D imaginary world. So, I mean, this is not what I use. I do this inside my mind, but if it helps a bit to represent it, this is like the same, well, it's similar to, it should be the same, but it's like, okay, this is a hexagon. Just assume that it's just a regular hexagon. And with this, what we can see, so here we have, let's say that this is our starting point, alpha. Now, if we do apply sigma, this is one rotation. So, okay, so let's do sigma. Whoop. Now we have applied one sigma. Now, if we apply twice sigma, we apply it again. Now we are in this spot. And we can keep applying sigma, which means that we are kind of rotating from point to point. And after 6 applications of sigma, we are back in the initial spot. Also, we can apply tau, which means that we are flipping the board, this reflection. And by flipping again, we are back because tau has order 2. Now, also, we could combine them. We could apply sigma once, and now we could flip the hexagon. And now we could also, again, we could apply sigma and flip with tau, and we are back to our initial point. We will see this as one of the Q-automorphisms that we analyze. So, okay. So I will put this aside. Now, what we're going to do is we're going to analyze all the intermediate fixed fields of this field extension, which correspond by the fundamental theorem of Galois. They correspond to the subgroups of this Galois group. So we'll change the page, the paper. Okay, so let's start by analyzing which subgroups we find by doing different combinations of all those generators, which are sigma and tau. I will write here on the side that sigma sends alpha to alpha multiplied by theta, and tau sends theta to theta minus 1, and then the other element is just fixed. And also this will be useful, we'll draw here the circle of the unit circle with all the roots that we had. So alpha squared to the, alpha theta to the square, alpha theta to the cube, alpha theta to the fourth, alpha theta powered to 5. Okay, and this is like, okay. Now, let's start by analyzing what happens when we, well, there is one which is, we already found it, which is that if you do tau, what you have is just flipping. So this is a group of order 2. This is the group integers modulo 2. And the fixed field of this, sorry about that, is, so we know that tau fixes alpha, so the fixed field of the group generated by tau corresponds to Q adjoint with alpha. Now, let's continue with sigma. Sigma has order 6. We know that sigma does all those rotations, so it has order 6. This is the group integers modulo 6. And the fixed field of sigma is theta. So this one was also straightforward. Now, let's do combinations, well, for the moment, iterations of this. If you do tau squared, you get basically the identity. You are back at the initial point. But if you do sigma squared, what you have is that from alpha, you apply sigma 1, 2 times. And so the first element that we see is alpha multiplied by theta to the power of 2. Now, if you apply sigma squared again, you land into alpha theta to the power of 4. And again, you land on alpha. So as you see, we have 3 elements. So this is a cyclic group of order 3, which is isomorphic. Well, this is the integers modulo 3. And then we need to find which is the fixed field. So we need to find what goes into here. So which is the element that is fixed by sigma squared? If you apply sigma squared to alpha, as we saw, as we've seen, you end up here. So this is not like a fixed. If you apply sigma squared to theta, what you will get is theta again. So theta is fixed by this Q-automorphism. But there is more. What happens? We'll draw a line. What happens if we apply sigma squared to alpha to the cube? As you see here, we are squaring. This is cube. When we combine this, we obtain that. So this is the same as applying sigma squared to alpha multiplied by alpha multiplied by alpha. And then when you apply sigma squared, what you get for each of those alphas is alpha multiplied by theta to the power of 2. So we have alpha theta squared, alpha theta squared, alpha theta squared. Then this is the same as saying alpha to the cube, theta to the 6th. And theta to the 6th, since theta is the primitive root of unity, the primitive 6th root of unity, this is equal to 1. So this is equal to alpha to the power of 3, which is what we had originally. So we see with this that alpha powered to the 3 is fixed by sigma squared. So we will place also here alpha to the cube. Now, okay, let's continue. What happens if we try to find sigma to the cube? Sigma to the cube means that we apply sigma 3 times. 1, 2, 3. We are here. 1, 2, 3. Back at the original. So we have only 2 elements. This is a group of order 2. It's cyclic. So this is integers modulo 2. Now, which is the fixed field? In a similar fashion that what we had here, now we are trying to find which is the fixed field. Well, which element is fixed by sigma to the power of 3. So here we played with the fact that when you multiply 3 multiplied by 2 gives you 6, and 6 cancels because it's just theta to the 6 is 1. So here we have 3, then we can try if alpha squared will give us back to alpha squared when applying sigma 3 times. So let's see, this is the same as alpha squared multiplied by theta 2 times and 3 times, because it's like the same that we did before, but now with alpha squared and sigma 3. So this is alpha squared multiplied by theta to the 6, which is again alpha squared. So alpha squared is fixed. And also if you apply sigma 3 to theta, by definition, sigma it does not have any effect on theta, so we will have also theta. So the fixed field of the group, the fixed field corresponding to the group generated by sigma to the cube is Q adjoint with alpha squared, and also theta is also fixed. Now we want to keep doing this till sigma to the power of 6, which is sigma to the power of 0, which will be the identity. But let's continue. Let's do sigma to the power of 4. Sigma to the power of 4 means that 1, 2, 3, 4, we are here. 1, 2, 3, 4, we are here. 1, 2, 3, 4, we are back here. So we have the same 3 elements that we had when we did sigma to the power of 2. The only difference is that now we are kind of going backwards. So applying sigma 4 to alpha lands us here, which is the same as applying the reverse of sigma squared to alpha, which is also going here. So this is not like a new group, subgroup. This is what we already had with this one. So let's write it here. Now if you try the same with sigma to the power of 5, sigma to the power of 5 goes here, and then at the next application goes 1 backwards, and keep doing this, which is the same as applying the inverse of just sigma. So we also will count this as a new subgroup. This is sigma to the 5. And then sigma to 0, sorry, sigma to the 6th is the same as sigma to 0, which is, it has the same effect as if you apply tau twice or 0 times, which is the same as not applying anything. This is the identity, and the fixed field of the identity is our like splitting field, Q adjoint with alpha and theta. Okay, so now we've covered the simple kind of Q-automorphisms, which only consist of just like each of the sigma and tau being iterated. Now we are going to keep growing this list by combining sigma and tau. We are going to analyze what happens when we apply this sigma tau combination. So we start from alpha, then we apply tau, we're just flipping, but alpha remains the same, and then we apply sigma. We are here. This is the first element. Now we apply sigma tau again. So okay, first we apply tau, look, it flips, we are now here, and then we apply sigma, and we are back in the initial starting point. So the 2 elements that we found are alpha and alpha multiplied by theta, 2 elements. So this is like order 2, which is isomorphic. Well, yeah, sorry, this is like the integers modulo 2. Now, which is the fixed field of this automorphism? So we are combining sigma and tau. The fixed field of tau and sigma were alpha and theta, respectively. So we know that probably doing some combination of them, let's see what we can find. So let's apply tau sigma to, for example, alpha theta. This first, we apply tau. Okay, so this is sigma of alpha theta to the power of -1 because we applied tau here. And now this is, so we apply sigma here. And then what sigma will do is this will be unaffected, but we will send alpha to alpha multiplied by theta. So we have alpha theta multiplied by theta -1. This cancels out and we have alpha. Alpha is different than the initial element that we had here. But we already see that, okay, so we start with alpha theta and we end up with alpha. What about if we apply sigma tau to alpha plus alpha theta? What will happen is that we will have sigma of alpha plus alpha theta to the -1. And now, when we apply sigma, we will have alpha multiplied by theta plus alpha multiplied by theta -1. This will cancel out, and we will have alpha multiplied by theta plus alpha, which is, this is the same as we had before at the entry point. So this is fixed actually. So this is the fixed field that we have corresponding to this subgroup, alpha plus alpha theta. Cool. Now let's keep iterating this. We are going to work now with sigma squared and tau, so that the combination of these two. So we apply tau, we are back here, and then sigma squared. Now we apply tau, and then sigma squared. So we have only two elements, alpha and alpha theta squared. So this is order 2, this is like integers modulo 2. Now, which is the fixed field of this? We are trying to find which element is unaffected by applying tau and then sigma to the squared. We know that when we were doing sigma not squared but just sigma, this is the fixed field that we found. The element that is fixed that we found, which then gives us the fixed field. What we are going to try is, okay, so what happens if we reuse the same element? Alpha plus alpha multiplied by theta. We apply tau, and then we have that we need to find sigma squared of alpha plus alpha theta -1. And then this is alpha multiplied by theta to the power of 2, because we are applying sigma twice, plus alpha theta power of 2 multiplied by theta -1 that we had here because we applied tau. Now, this is not the same as this one, but what we can see is that if we had here -2, then this will cancel out and we will have here something similar to the initial shape. So what about if we put here -2? This should come from here having -2. And having here a -2 means that when we apply tau, we are applying it to theta to the power of 2. So when we have alpha plus alpha multiplied by theta to the power of 2, then it actually ends up landing into alpha theta to the power of 2 plus, and this is just cancelled, this is alpha, and this is the same as here. So this is actually like the fixed field that we needed. So Q adjoined with alpha plus alpha theta to the power of 2. Now let's keep going. Sigma squared tau. This means that we applied, okay, tau from alpha, we apply tau. We are still in alpha. And now sigma to the cube. 1, 2, 3. We are here. Now here you apply tau and then sigma to the cube. You are back here. So this is order 2 again. Now, which is the fixed field? There is one detail that I haven't said here, is that in the previous one, when you do sigma squared tau, we could also use here alpha theta, because if you unfold this, you have sigma squared of alpha theta -1, and now this will be alpha multiplied by theta squared multiplied by theta minus 1. And this is the same as alpha theta, which was the original also same. So here we can also say that alpha theta. Okay, so let's go back to where we were. We have now sigma to the power of 3 multiplied by tau. So we are going to iterate over this thing that we had here. Let's try if this works out. Spoiler, yes. So alpha plus alpha multiplied by theta to the power of 3. Now we apply tau. We have sigma to the 3 of alpha plus alpha theta to the power of minus 3. And then now applying 3 times, we have alpha theta to the power of 3 plus alpha theta to the power of 3 multiplied by theta to the power of minus 3. This cancels out and we have the same here. Okay, so this is the fixed field. This is a cube. Now sigma to the fourth. Sigma to the fourth is applying and tau combined. So we apply tau, we are still in alpha. Now 1, 2, 3, 4, we are here. Now you apply tau, and then 1, 2, 3, 4, back here. Order 2, again. So this is the integers modulus 2. Now the fixed field here, it's very similar to what we had before. So we can use, similar to before, alpha plus alpha multiplied by theta to the power of 4. This will give us the same as we have been getting in the previous iterations. And also we can use a variation of this one, which is alpha theta squared. This will also give us alpha minus 2, theta to the minus 2, equals to alpha theta square to the 4 multiplied by theta minus 2, which is alpha theta squared, which is what we had initially. Okay, so here we can choose alpha plus alpha theta to the 4, but also alpha theta squared. All right, now sigma to the fifth, tau. So you apply tau and then 5 times sigma, you are here. Now you apply tau and 5 times sigma. 1, 2, 3, 4, 5. You are back here. So it's another group, cyclic group of order 2. And as you can imagine, we could try to check it, but just we see that the pattern, that the fixed field will be Q adjoined with alpha plus alpha theta to the power of 5. Okay, so we have another batch of those Q-automorphisms. Now we already covered all the combinations of like applying the sigma and then tau, or tau and then sigma, which is kind of similar, although it's a non-abelian group, so it's not the same doing sigma tau than tau sigma with some of the iterations. This is a property of the dihedral groups. And then what we are going to keep combining now is more of what we have as similar to the dihedral groups, which is like first, so you have this sigma and tau. Now sigma has order 6 and tau has order 2. So the order of all this stuff is 6 multiplied by 2, which is 12. And this is the dihedral group of order 12, actually. And the fixed field of this is just Q. Now, let's iterate this. We're going to use sigma squared tau. We don't square tau because we know that tau squared is again the identity. So, okay, so sigma squared has order 3, as we saw before. In fact, it's here, order 3. Tau has order 2, so 3 multiplied by 2. This is 6. This is the dihedral group of order 6, D3. Now, which is the fixed field by this that corresponds to this subgroup? So if you apply sigma squared to where it was, sigma squared to alpha, you will get again sigma squared. If you apply sigma squared to tau, you will also get sigma squared, because tau does not affect, it just fixes whatever alpha variation. So the fixed field here is alpha to the cube, because if you apply, let's write it, sigma squared to alpha to the cube, what you get is what we have actually here is you end up having alpha squared multiplied by theta to the power of 2 multiplied by 3, which is 6, which means that you have alpha multiplied by, alpha squared multiplied by, this is 1. And then if you apply, if you apply tau to alpha to the cube, tau just fixes alpha, so you also have alpha to the cube. All right, let's keep iterating. Now we are going to use sigma to the cube and tau. Sigma to the cube is like doing 1, 2, 3 and 1, 2, 3. This is order 2, and tau also has order 2, which means that here we have 2 multiplied by 2. This is 4. And this is the dihedral group of order 4, which we denote as this D2. And the fixed field here will be Q adjoined with alpha to the power of 2. All right, now if we try to do sigma to the power of 4 combined with tau, this is the same as we had here. So this is, as we saw before with sigma to the 4 is kind of isomorphic as sigma to the 2. So here it's like similar. So this is not a new group. In fact, this will go here. And then if you try to do sigma to the 5 combined with tau, like if you try to find this dihedral kind of group, this is also something that we already had, which is here. So also this is not a new group. So sigma to the power of 5, we saw before that is like the same as just applying sigma but going backwards. So it's what we already have here. All right. So now we are still missing some Q-automorphisms, which we already exhausted these kind of combinations. Now we are going to do another kind of combination again, which is, let's do, so we already have so we are going to do sigma squared combined with sigma tau. This is like a combination of the combination. I'm going to draw here again the unit circle with the roots, because it's useful to have this visual support. All right, so we know that sigma to squared has order 3, because it's like sigma squared, sigma squared, sigma squared. This is 3 multiplied by the order of the tau sigma. Tau sigma, we saw it earlier here, has order 2. Tau sigma is applying, okay, I apply tau, we are here, and then sigma. Now I apply tau and then sigma. So it's like just two elements. This is 6. This is the dihedral group of the dihedral group of order 6, which is D3. And the fixed field for this is a bit of more involved. So how do we find this? Let's apply. So we know that the fixed field of sigma squared from earlier, the fixed field is alpha to the cube and also theta. And the fixed field of sigma tau is alpha plus alpha multiplied by theta. So kind of we can combine this thing with this thing. Let's see how this goes. So let's find alpha to the power of 3 plus alpha to the power of 3 multiplied by theta. Let's see. So here we will have alpha to the 3 and then theta to the 3 multiplied by 2 plus alpha to the 3 multiplied by theta to the 3 multiplied by 2 multiplied by theta. This will be equal to 1 because this is theta to the 6 and this is also equal to 1. So what we have is alpha to the cube plus alpha to the cube theta multiplying. This is the same as we had before, but we also need to make sure that this is fixed by this other Q-automorphism, which is tau and sigma. Let's see. Alpha to the 3, alpha to the 3, theta. Now, okay, we apply tau. We get that we need to find sigma of alpha to the 3 plus alpha to the 3. And here we have minus 1. And now you apply sigma. This is from before. We apply sigma and we have alpha to the 3 multiplied by theta to the 3. This is just like applying sigma to alpha cube. And then here the same multiplied by sigma minus 1. This is not going to disappear. So then this is not fixed by this Q-automorphism. So this is not what we want. But actually, check what happens if we try here putting a 3. This means that before we had a 3 here. Now this disappears. And if we had a 3 here, this means that here we had a 3. So now this part, because this is alpha to the power of 3 multiplied by theta to the power of 3 plus alpha to the power of 3. This is the same as here. Would this also work, this element like alpha to the power of 3 plus alpha to the power of 3 multiplied by theta to the power of 3? Would this work also in the previous try of the automorphism, sigma to the power of 2? So if we put here a 3, what happens? So this is still the same, this is the same, then here we have a 3. Then here we have a 3, which is the same as we had here. Thus, the fixed field is Q adjoined with alpha to the power of 3 plus alpha power of 3 multiplied by theta to the power of 3. We found it. Now, let's find the remaining couple of Q-automorphisms. One is iterating from here, sigma to the power of 3 multiplied by sigma tau. This is like, so sigma to the 3 is just going here and then going here, going here, going here. This is order 2. And then we know that tau sigma is also order 2. So 2 multiplied by 2. And actually, this is the same as having this, I think they call it Klein group. This is theta, which is, this is isomorphic to theta 4. Now, the fixed group of, the fixed field, the fixed field of this, which is the shape of this. We know that before we used, so we had sigma squared and we have here alpha to the power of 3. So let's try using alpha squared plus alpha squared multiplied by theta squared. what happens if we apply sigma squared here? What we obtain is alpha squared multiplied by theta to the power of 2 multiplied by 3. This is 1, so we can just cancel this, plus alpha squared multiplied by theta 2, and then when we apply sigma 3 times, we get here also theta to the power of 3 multiplied by 2. This is also 1, which gives us alpha squared plus alpha squared multiplied by theta squared. And from before, we know that when you apply sigma tau here, you also end up having alpha squared plus alpha squared theta squared. So this is the fixed field, alpha squared plus alpha squared theta squared. But there is more. If you try also, you can see that alpha squared theta squared also this is a fixed field. And now for the last one, we're going to combine sigma cube and sigma squared tau. This is, okay, so this is order 2 multiplied by this thing here is what we had earlier before, which also has order 2, which is 4, this was 4, sorry. And then this is also zeta 4. And then which is the fixed field for this? In a similar fashion, we have alpha squared theta to the 4th.